Industrial manufacturing requires humans to interact with forces capable of destroying them. Operators work inches away from high voltage, corrosive chemicals, and massive kinetic energy. Safety engineers neutralize these threats using a foundational equation: hazard plus exposure equals an accident. In heavy industry, the hazard itself, the voltage or the pressure, is often a requirement of the process and cannot be removed. However, if the exposure variable can be forced to drop to zero, the accident is mathematically eliminated. This objective is achieved through a layered architectural defense system designed to isolate the worker from the inherent dangers of the machinery. Civilian safety models often focus on managing the worker through rulebooks, training programs, and constant warnings. But human behavior is the most volatile variable in a factory. Factors like fatigue, distraction, and habituation make an operator's memory an unreliable primary defense against injury. To maintain a reliable environment, engineers must first alter the physical machine and the workspace layout. The goal is to neutralize the threat before it ever reaches the human operator. By shifting the burden of safety from the worker's vigilance to the environment's design, engineers remove the opportunity for a simple lapse in judgment to become a fatal error. This strategy is known as engineering controls. These are physical modifications to the workplace that address a hazard at its source, regardless of how an employee behaves. The baseline strategies are substitution and design. This involves replacing a toxic chemical with a stable one, or re-engineering a workstation to be ergonomically correct and inherently safe. Some hazards are unsubstitutable. In this mechanical press, the massive exposed gears and crushing surfaces are essential to its function. They cannot be designed away. When the hazard must remain, engineers use enclosure. This is the complete physical containment of moving parts or toxic liquids during normal operations, sealing the danger away from the operator. If the machine requires material to be fed into it, full enclosure is impossible. In these cases, engineers install barriers to prevent physical access to the hazard zone while the machine is active. For invisible threats like toxic vapors or dust, ventilation is used. This industrial hood is positioned to pull hazardous airborne exposures directly away from the work zone before they can be inhaled. Collectively, these 5 strategies serve as a physical wall, separating the worker from the most dangerous aspects of their environment. Physical engineering controls have practical limits. Some hazards cannot be barricaded or enclosed while still allowing for human maintenance or operation. When physical barriers are insufficient, industry relies on a rigid vocabulary of visual linguistics to govern behavior. These signs are precise classifications defined by OSHA and ANSI standards, designed to communicate specific levels of severity at a glance. The danger classification is the highest tier, indicating an immediately hazardous situation that will result in death or serious injury if ignored. Orange warning signs indicate a potentially hazardous situation. While the risk may not be as immediate, the outcome could still be death or serious injury. Yellow caution signs mark potential hazards that may result in minor or moderate injury, serving as a reminder against unsafe work practices. Other indicators provide operational data. Notice signs state company policy, general safety signs outline procedures, and red and white fire safety signs identify equipment locations. This standardization translates risk into visual commands, providing clear direction in moments where human judgment might be compromised by stress or urgency. In a chemical emergency, first responders must identify hazards before they can safely approach. They only have seconds to understand the chemistry of a leak. Responders use the NFPA diamond, a specialized visual tool built specifically for rapid hazard identification in high-stakes environments. The system uses a numeric scale from 0 to 4. In this matrix, higher values always indicate a more severe threat. The blue field represents health hazards, and the red field represents flammability. A 0 indicates a stable material that will not burn, while a 4 indicates a deadly substance that ignites below 73 degrees Fahrenheit. The yellow quadrant indicates reactivity. This scales from a 0 for stable chemicals up to a 4 for materials capable of detonation under normal conditions. The white field is reserved for special hazards. It uses specific codes to warn responders of corrosives, oxidizers, or radioactive materials that require unique tactical responses. The NFPA diamond functions as a multivariable data matrix, allowing responders to make tactical decisions based on the specific chemistry of the scene. These codes and machines form a single cohesive framework for industrial survival. First, engineers modified the physical environment, using barriers and ventilation to remove as much exposure to the hazard as possible. Where physical barriers end, standardized visual linguistics take over. ANSI classifications and NFPA data provide the information necessary to regulate human interaction with any remaining threats. By addressing both the physical environment and the operator's perception of risk, this layered system attacks the exposure variable from two sides at once. Industrial safety integrates these engineering and visual controls to manage the risks inherent in manufacturing. This transition from raw hazard to designed safety turns dangerous workspaces into environments with calculated and manageable risks.